In episode 1, we agreed the problem. Isolation that depends on every query, remembering a filter is not a security model, it is a hope. So here is the fix. Postgres can apply that filter itself on every query, whether you wrote it or not, whether the query came from your API or from a PSQL session someone opened at midnight. It is called row-level security. And once it is on, the query I showed you in episode 1, the one with no tenant filter, returns exactly the rows it should, and nothing else. This episode is how it works, and more importantly, the 3 ways it silently does nothing while you believe you are protected. This is the whole mechanism. You enable row-level security on the table, and then you write a policy. The using expression is a condition Postgres silently ends onto every query that touches this table. So a select for unpaid invoices becomes, invisibly, unpaid invoices, where tenant ID matches the current session's tenant. The developer does not write it. The developer cannot forget it. And notice the with check clause, which people leave out and then regret. Using controls what you can read, with check controls what you can write. Without it, a tenant cannot read another tenant's rows, but can happily insert a row stamped with somebody else's tenant ID. Reading is the leak everyone thinks about. Writing is the one that corrupts. That policy leans on current setting, which is just a variable on the database session. So the question becomes, who sets it, and can it be trusted? Your application sets it per request from the tenant it resolved after authentication, never from anything the client sent. And that is the whole ballgame, because a tenant ID in a request header is an ID the caller chose. And use set local inside the transaction, not set. The difference matters more than it looks. Set local is scoped to the transaction and reverts when it ends, while a plain set lives on the connection, and connections go back to a pool and get handed to the next request, which might belong to somebody else. That is episode 4's problem, and it is how a perfectly correct policy leaks anyway. Now the part that costs people real money, because all 3 of these look like RLS is working. First, and this is the big one, the table owner bypasses their own policies. Postgres exempts the owner by default. So if your application connects as the user that created the tables, which is exactly what the average migration setup does, your policies are decorative. You need force row level security, or better, an application role that does not own anything. Second, superuser and any role with BYPASSRLS ignores policies entirely, which means your admin tooling and your background jobs are almost certainly not protected. And third, a table with RLS enabled, but no policy denies everything, while a table you forgot to enable it on allows everything. And those 2 failures look nothing alike in production. Which is why the last step is not writing the policy, it is proving it. And this is the part that turns a security questionnaire from a creative writing exercise into a link to a test. Write a test that sets the session to tenant A, queries for a row you know belongs to tenant B, and asserts it gets nothing back. Not that it errors, that it returns 0 rows, because that is the actual promise. Run it as the real application role, through the real connection path, because a test that runs as a superuser proves nothing at all. Then do it for insert, update, and delete too. It is a handful of tests, it runs in seconds, and it is the difference between believing you are isolated and being able to demonstrate it to someone whose signature you need. So the engine now refuses to cross tenants, as long as it knows which tenant is asking. That turns out to be a much harder promise than it sounds, because that answer has to survive authentication, a connection pool, a background job, and a message queue, and it gets dropped at every single one of those. Next episode, tenant context, and everywhere it goes missing. See you there.